Good morning. Let us see today what are buffer solutions. What are the types of buffer solutions? What is buffer action? Okay, and we will derive the Henderson-Hasselbalch equation to calculate the pH or pKa or salt concentration, etc. Now let us see what are buffer solutions. Buffer solutions are solutions which resist the change in the pH by the addition of acid or base. On the addition of acid or base to the solution, there is no change in pH. For example, sodium chloride solution. Let us take sodium chloride solution. It is not a buffer solution. Whereas ammonium acetate solution, you prepare ammonium acetate solution, it acts as a buffer. Why it acts as a buffer? Whereas sodium chloride is not a buffer. Let us explain now. Sodium chloride and ammonium acetate are strong electrolytes. They are completely dissociated. Okay. By the addition of acid, the added H plus ion combines with the acetate ion to give weakly, feebly dissociated acetic acid. Therefore, the added H plus ion is removed as weakly dissociated acetic acid. Therefore, there is no change in pH. Whereas, when you add acid to sodium chloride solution, Cl minus ion H plus similarly gives H plus and Cl minus HCl. HCl is very strong acid, strong electrolyte, is completely dissociated. Therefore, H plus, the added H plus ion will remain there. It is not consumed by acetate ion or here there is Cl minus ion. It is not consumed. It is not taken up by Cl minus ion. Therefore, there is increase in pH. There is decrease in pH because of the addition of acid to sodium chloride solution. Let us consider addition of base to sodium chloride solution and separately ammonium acetate solution. Okay. On adding OH minus ion, it combines with the NH4 ion present in the aqueous solution to give undissociated weak base. Therefore, the OH minus ion is taken up, is removed by the ammonium ion to form weakly dissociated ammonium hydroxide. Therefore, there is no change in pH. There is no increase in pH as a result of addition of base. Similarly, Na plus OH minus ion combines to give sodium hydroxide, but the sodium hydroxide formed is a strong electrolyte and also a strong base. It is completely dissociated to give Na plus OH minus ion. Therefore, the OH minus ion is not consumed, is not taken up, is not removed by Na plus ion. Therefore, there is a significant drastic increase in pH. Okay, now let us see what are the types of buffer solutions. There are two types of buffer solutions: weak acid and its salt, and weak base and its salt. Weak acid, acetic acid and sodium acetate, carbonic acid and sodium bicarbonate. This is the buffer in body fluid and in blood, etc. Very important to maintain the pH of our body, pH of our blood. And ammonium hydroxide and ammonium chloride. Buffer solutions has lot of applications. For example, it is used in cell growth, fermentation process, medicine, and several industrial process, and also in several chemical reactions. Let us see buffer action. How does it resist change in pH? What is the mechanism involved in buffer action? In aqueous solution, the following ionization equilibrium process take place. Okay. For example, weak acid in the aqueous solution, it undergoes partial dissociation to give its ions. There exists an equilibrium between undissociated acid and its ions. Okay. Whereas the salt sodium acetate is a strong electrolyte, it is completely dissociated to give acetate ion and Na plus ion. Now, in the presence of, remember, in the presence of acetate ion, in the presence of excess, it is completely dissociated, there is excess of acetate ion. Therefore, in the presence of excess acetate ion, due to common ion effect, because of the excess of acetate ion, the equilibrium will shift towards left. The equilibrium will shift towards left, so that therefore most of the acetic acid is undissociated because of the common ion effect. The degree of dissociation is suppressed. What is common ion effect? The degree of dissociation is suppressed by the addition of common ion is called common ion effect. So, in the presence of excess of acetate ion, the dissociation of weak acid is suppressed. Okay. Now, on the addition of acid, H plus ion, the added H plus ion combines with the acetate ion to give weakly dissociated acetic acid. Similarly, there is no change in pH. Okay, it resists change in the pH by the addition of acid. On the addition of base, the following reaction takes place. OH minus ion reacts with H plus ion to form water. Therefore, this equilibrium is disturbed because since we are removing the H plus ion, one of the product, therefore the equilibrium will shift towards right. To maintain the equilibrium constant, according to Lee-Chaltier-Brown principle, the equilibrium will shift in such a way that there is no change in the equilibrium. Therefore, to maintain the equilibrium constant, okay, the equilibrium will shift to the right according to Lee-Chaltier-Brown principle. Okay. Therefore, there is no change in, therefore the H plus ion concentration is maintained because of the equilibrium shifting towards right. Okay. Now let us see, for example, weak base and its salt. The following process takes place, the following reactions takes place in aqueous solution. On the addition of base, OH minus ion combines with the ammonium ion to form ammonium hydroxide. We have shown here. Therefore, the ammonium hydroxide formed is weakly dissociated. Therefore, there is no change in pH on the addition of base. Similarly, on the addition of acid increases the H plus ion. The added H plus ion reacts with the OH minus ion to form water. Similar to here, what will happen? The equilibrium will shift towards right, so that to undo the changes, to maintain the equilibrium constant at particular temperature, according to Lee-Chaltier-Brown principle, the equilibrium will shift to right, so that the OH minus ion concentration is constant. Therefore, the pH does not change as a result of addition of either acid or base. Okay, we have studied now buffer action. Now let us derive the Henderson-Hasselbalch equation, which is used to calculate the pH of the buffer solution and also the dissociation constant and also ratio of salt to acid concentration. Okay, if you know pH and pKa, we can calculate the salt concentration, acid concentration. If you know the ratio of salt and acid concentration, then we can calculate, if you have pH meter, then we can calculate Ka. Okay. Okay, now let us, how it is derived. Consider weak acid and its salt. Weak acid is partially ionized as shown here. Applying, this is an equilibrium process. Let us apply the equilibrium constant. Let us apply the law of mass action. Applying the law of mass action, the equilibrium constant is obtained. Ka equal to concentration of product divided by concentration of reactant. Since we need to calculate the pH, the H plus ion concentration is taken out. Therefore, acetic acid will come here and acetate ion will come here. Since, as I said, due to common ion effect, acetate ion, acetic acid is not dissociated at all. Therefore, the acetate ion contribution comes only from the salt. Therefore, this will be taking negative logarithm to the base 10 of H plus ion and the negative logarithm to the base 10 of Ka, and the log I interchange because plus or otherwise minus, plus log, this is, as I said earlier, salt concentration and divided by acid. Therefore, pH equal to pKa plus log to the base 10 salt by acid. Similarly, you can write for ammonium weak base and weak salt. You can obtain pOH equal to 3 Kb plus log to the base 10 salt by base concentration, where Ka and Kb are the dissociation constant of weak acid and weak base respectively. So several problems were asked based on, several questions were asked based on the mechanism of buffer action and the Henderson equation. Please write down the formula, please understand and write down the formula. Thank you for watching.